Hello, welcome to a problem session. Today we have an interesting problem. So let's look at the problem and then we can try to solve it. See if you can come up with some answer, and then you can look at my solution. Okay. So this is the problem where I'm going to just refer to the figure. As the figure says, there is a block here. Its mass is m, and it's attached to a spring and hanged, so it's kind of at equilibrium. But the block actually moves in a fluid, and so fluid has a viscous force. If the block is moving down, the viscous force will be up, and it will be denoted as BV. So B is given, K is given, M is given. So it's a ordinary setup for damped oscillator. Then the hard part is that at t equal to 0, it's whacked by, and it's a very instantaneous force. So this is the way you can deal with describe instantaneous force. So Ft is instantaneous force. And so if you look at T like this, if you look at what's the instantaneous force, it's going to be something like that. This is F with a T. But then you can see that it's got some, you can model it like that. So it at 0, it's delta T over 2, and this is delta T over 2 negative. But you know, a force like this area is what we call impulse. So the area is, you know, you can if you were to use this type of approximation, and if this was, say, F0, then you have F0 delta T will be the impulse P0, but it's not the case actually. F0 is not some fixed value, because delta T is, you can do another approximation. If you make it delta T small, you have to really raise it to this high to get the same area. So this is like a new F0, and new approximation, F01. And now this delta T over 2 is the 1, delta T 1 approximate is still P0. So you can see this is not the same as that. So it's a kind of a way to deal with it. You can say that the area is same because the impulse is the same. In that case, I need to take a limit delta T goes to 0, and we can if we deal with F0 delta T, then F0 goes to delta T goes to 0. So when F0 goes to infinity, then this is kind of nonsense, but we require F0 delta T equals to P0 remains. So this is one way to look at what is called Dirac delta function. Another way is this, think in terms of integral. So if this is a delta function, so if you look at that way, P0 delta T dt, and that's going from minus infinity to infinity, and P0 is constant, so it comes out. So P0 minus infinity to infinity delta T dt, and this is the P0 is the impulse, and this is the F dt. So this is equal to, this integral is equal to 1. This integral equals to 1. This is another way to think about Dirac delta function. That makes it you can only think in terms of inside an integral, so you have to integrate it somehow. That's a explanation of the problem. setup and the difficulty that lies. I can just tell you that the problem at t less than 0, there is t less than 0, it being addressed. So x has been 0 and dx dt has been 0. That's another thing given. So we are to find t greater than 0. So if you look at this t equal to 0, t greater than 0, the equation is m d square x dt square plus gamma b dx dt plus kx equal to 0, because once t is greater than 0, and if taken delta t goes to 0 limit, and this only at time 0 will remain very infinitely high, but time 0 will remain. So this is the case, and at t equal to 0, undefined, because delta t is at t equal to 0, it's infinite, equals infinite at t equal to 0. So we don't have a defined. If you write the equation formally, it's going to look like this: m d square x dt square dx dt plus kx. So at t equal to 0, it's going to look like p0 delta t. So we need to know how to deal with it. So we learned about integrating. Maybe this has to be integrated to get to the answer. So I will come back and try to solve it. Okay, you can pause it, and I'm going to erase this and come back and solve it. Okay, so before I completely solve it, if you like these kind of videos that I'm making, very correct and complete solution of some of the problems, you may want to hit the like button and things like that. Or you want to check out www.physicsbootcamp.com, bootcamp.org actually. That's the website I maintain. Describe a lot more concepts and more detailed ideas. All right, so let's look at the solution. So at t equal to 0, all t, the equation of motion will be m d square x dt square plus b dx dt plus kx. This is 0 for t greater than 0, and m d square x dt square plus dx dt plus kx equal to p0 delta t for all t, because this kind of describes in a formal way. Okay, and x at 0 is 0, and dx dt at 0 is 0. So these are given. So first thing to notice is we're told that it is a underdamped. So if you just kind of get rid of b, and then it's gamma, and this is going to be omega 0 square. So it's given gamma over 2 is less than omega 0. That means underdamped. So without any problem, we can say that it's going to be, solution will be for t greater than 0, solution will be x of t will be some a e to the power minus gamma over 2t, and because we are going to have x of 0 has to be 0, we will have a sine of omega 1 t, and omega 1 will be just square root of omega 0 square minus gamma over 2 square, as usual for damped oscillators. So we're gonna, so only thing remaining is to figure out what this will be. That's the problem only. So this is the only thing we need to figure out. It satisfies this, and it satisfies okay, so it satisfies this using that. So we have satisfied that, and this one we will use, this is the 0 minus, is velocity before, and this is so what we have said is x 0 plus is x 0 minus, which kind of makes sense. There's no time elapsed, so it's going to be in the same. The velocity can actually be different in the before or after, because the impulse, delta function impulse. This does not mean that velocity 0 plus equal to velocity 0 minus. So this one is in position is in the same place. So this is using this, we made sure that this is sine and not cosine. Okay, so this is our going to be hypothesis, and let's see. Now I'm going to deal with this equation. As I've said earlier, you can integrate it because we need to integrate it because of that. So let's integrate it. So I'm going to integrate this whole thing dt. I'm going to integrate from minus delta t over 2 to delta t over 2, and then I'm going to take a limit delta t goes to 0. Okay, and I'm going to do the same thing on this side, minus delta t over 2 to delta t over 2, and I'm going to take a limit delta t goes to 0. So on this side, let me get a little bit better ink. So on this side, I'm going to get a limit delta t goes to 0, p0 times 1, which is just p0. Here, notice I'm going to have something from here, and something from here, and something from here. So let's look at each term at a time. So let's look at kx. So you have a kx dt. Okay, so, and this is minus delta t over 2 and delta t over 2. A limit delta t goes to 0. The case constant, and so this will be 0 because nothing goes like delta function here, or no integration by parts. How about this guy? Dx over dt, and we have a dt, and you have a b, and delta t over 2 and delta t over 2. So this is equal to b x at delta t over 2 minus x at minus delta t over 2, and I'm supposed to take a limit delta t goes to 0, and these x is going to be the same place. So this is b at x 0 plus minus x at 0 minus, and this is, they're equal to each other. So these two kind of go away. And how about that? This one is going to be, let me take a clean up and get more space. Okay, so the right side is gives me p0, and then says 0 plus 0. How about that guy? That guy, let's work out m d square x dt square dt. So we can think of this as a d over dt like that. So dt cancel out. So this is m dv, and so this goes to m v at 0 plus minus v at 0 minus. So this goes taking a limit delta t go to 0 limit on this whole thing, gives me that. So this just is a m, and v0 minus is 0. This is the v0 minus is 0, so v0 is plus. So this is looks like a v0 plus minus 0 and m. So the impulse just actually gives us the velocity, because it was at rest. Just this is the new momentum, right? We could have guessed that right from the get-go. So if you look at that, and I can use that into this to figure out what A has to be. Okay, so what we found is mv at 0 plus is going to be the momentum afterwards. That's the impulse, the change in momentum. I really didn't need to do all this integration. I could have guessed that right from the get-go, right? So this somehow I need to put in there. So how do I get it? If this is my hypothesis for what the x looks like, I just take a derivative of that, and this is already t greater than 0. So I get v at t greater than 0 is equal to a e to the minus gamma over 2t, and it's going to be minus gamma over 2 sine omega 1t, and then I take a derivative of that. It's going to be plus omega 1 cosine omega 1t, take a derivative of that. And so v at 0 plus from this is going to be a, and this is times 1 times 0 because the sine, and the cosine give me 1, that's omega 1. So actually a is equal to v at 0 plus over omega 1, which just p0 over m, p0 over m omega 1. So we got an A. So this is my answer. So the answer would turn out to be x for t greater than 0 is equal to p0 over m omega 1 e to the minus gamma over 2t sine of omega 1 t. That's the answer. You can extend this problem, and I would say suppose it was oscillating, and you did apply the impulse not on rest, something at rest, but was oscillating, and then you hit it. Okay, that's going to be a more complicated expression, but same physics will apply. So what you when you apply an impulse, you use change in momentum that will result from that impulse, and you can show that by actually integrating the whole thing. Okay, I think that's for now. I'll see you in another video. Bye.